show of hands of how many people want to come out and socialize and so on. 1, 2, 3, 4. This is quite good, actually. 1, 2, 3, 4.
There's a double over there.
Oh. Yeah, okay, so this is good. Great. We look forward to that, and we'll sort out the details. In the meantime, I'd like to introduce Antonio Gutierrez.
That's fine. Don't worry about it.
Close enough, sorry. Who's going to tell us a little bit more about GRBs, and
All right.
I leave it to you. And did you get the microphone? Because
Yes.
otherwise, we'll not
Got like that? Okay. Can you hear me now? Yep. Okay. All right. So thank you much for giving me the opportunity to talk about what happens after all Judy's work, essentially. So most of the things we're talking about so far has been happening up here. I put up Swift and Fermi over here. Essentially, they detect the gamma ray burst. My job starts from here on. Essentially, when the message comes down where the position, what happens after that? And I work from the ground-based community, and I will tell you more about this, and I will hopefully I will sparkle some interest on do some science as I do. So I know Judy for 9 years. We were both graduate students, and GRBs were awesome. So we were like, with telecons, computer, running from a grocery store while talking to people about the GRBs happening here and there. After 9 years, we look like more like this. Not exactly quite the same, but yeah, so last night I was like this. Anyway, so bottom line, when the position comes down on Earth, what can we do? The community has been growing for the last 20 years. Now there are lots of facilities that can be used, that we can use, to study gamma ray burst afterglows in all the low energy bands, from optical, near-infrared, radio, light groups. And one of the main goals is understanding about the progenitor. But what else? Well, I point is only 4 of the main topic. One is because we can determine the redshift of these gamma ray bursts, which are crucial not only for for gravitational waves detection, but also because gamma ray bursts are probably connected with the first stars. How do we know if they are the first stars or not? We need the redshift. The afterglow can be observed in spectroscopy, and there are some absorption lines that are detected which provide information about the interstellar medium. And in the same way, other absorption lines that are arising from material between the GRB host galaxies and us give us information about the intergalactic medium. And finally, when the GRBs are gone, there's no optical emission anymore, we can go back and study the galaxy where these GRBs live in, because if GRBs are one of the first stars, their galaxy might be some of the first galaxies. So we are interested in looking at those, and we studied their properties. I just mentioned Medalisti over there. So 10 years of data. We have tons of data now. The GRBs, we have more than 300 GRB spectra. And so this is the nightmare, everybody. We want data to understand this phenomenon. We need data of any kind, from any sources, any wavelengths. And in fact, now we do have a lot of a plethora of spectroscopic data that have been not published because they look not interesting as a single object, but now we have a collection of those. So we have a lot of this information sitting in someone's archives, databases, in the United States and Europe that are ready to be looked at, and hopefully there are a lot of opportunity for small projects. I am part of international collaboration. I am sitting in an office at Goddard Space Flight Center, but I work with people at Harvard, Caltech, East, West, Europe, and so on. We do have access to prime facilities. These are the biggest telescopes in the world. And also there are people working with me and some senior researchers at Goddard that have access to small robotic facilities that, again, provide other information. So please talk to me if you're interested in learning more about this. Let's go about science. As I said, redshift determination. Remember, GRBs goes off. We get text messages, phone calls. I talk to my guys in Hawaii, get the imaging of the GRB. And this is one particular case where we have, these are infrared band, Y, J, H, and K. And this is a gamma ray burst of 9423. And you can see there is nothing in this image. But then when you go in the infrared, you see an object. This is a clear signature of a high redshift event. For this particular one, in 2009, we were able to go on the spot and observe with the spectrograph the emission. And we get this crappy spectrum here And this is so crappy because it was observed only a day after. Okay? This spectrum confirmed the fact that there is flux in the J, H, and K band, as you were imagining from the first night imaging, and there is almost no flux in Y and Z, which essentially put these objects among one of the farthest single object ever observed, spectroscopically observed. Okay? So this is one case of a Nature paper from Nigel Tamvir. 5 days later, or actually 6 days later, this other object came up. Oh man, two objects like this in the same week is a nightmare for everybody. This is even farther in redshift, the same image like before. You see now it's detected in the H and K, maybe something in J, nothing in H. This time we were not so lucky. It was my longest night in my 10 years of gamma ray burst science. Clouds cover Gemini North when I was going to ask for a spectrograph, or a spectroscopic observation, so I couldn't get anything. And the night after was already too faint. But still, we could have worked out a photometric redshift of 9.4. So this put this object at 500 million years after the Big Bang. Okay? And so this is a contour-plot. You can do something like this. So again, just based on very, one night of data, you can observe objects that are only 500 million years old. Again, so gamma ray bursts lead our way to exploration of the early universe. They are massive, so probably they are linked to the first generation of stars, or maybe the early second generations. And finally, what I mean when I say spectroscopy is cheap, high rewarding, and secure technique, I mean this. Those GRBs, to determine their redshift and understanding what they are, took us essentially 7 days of data. If you want to do that with Hubble, it takes us this amount of time. So GRBs are right here. This 9423 is right here, GRB 9429b is here. To get to this point, you have to have 10 years of data from Hubble in the same small part of the sky for 10 years with the best camera ever. So that's what I mean. Not only that, now we have many more GRBs at high redshift that we can study, and many more will come. So that's what I'm saying. Like gamma ray bursts are your best way to observe the first generation of stars and galaxies and understanding the property of those objects. Again, when the GRB goes off, this is a kind of a crude approximation, goes off in an H2 region. So when explodes, the afterglow emission before getting to us, these are my favorite Gemini telescopes, north and south. This emission, the afterglow emission, passed through the material and leaves some imprint in the afterglow, in particular in the spectrum. So this is a spectrum of 50730, and you can see all these absorption lines here. These are all material that stays between the GRBs and us. In particular, some of these belong to the interstellar medium, which is nearby the GRB. If I go farther, if you can imagine, there is GRBs, there's a galaxy limit. There are some pockets of other stuff in between. They are still in the galaxy, but are not close to the GRB. And these also, this is called IgM, leave some imprints. Actually, this is still ISM. Leave some imprints in the spectrum, and we can study those. So we can actually probe all this material around here. And finally, there are galaxies in between that absorb the light again, and those also appear in our spectrum. So you see, with one single data set, we probe many different scales of the galaxy itself and the line of sight. Now again, we have a lot of data. These are one of the best spectrograph available. There are databases that have data up for grabs, and we do have all the expertise in hand, in-house to process all this data. We just need to find the time and people that would like to do something with it. One of the things that we can study again is the neutral hydrogen content, and this is an example. So this is the H1 line, Lyman alpha line for 110205A. You see this broad feature here. The broader the feature, the largest amount of neutral hydrogen is near the gamma ray burst. And we know the stars form from cooled neutral hydrogen gas. So you can imagine immediately that if you want to study star formation regions, you need to understand what the reservoir of hydrogen is there. And these are a few other examples. And this is a recent paper of Ryan Chornock on 13606A, where he sees this narrow H1 column density but then each different colors belong to a different galaxy, a different absorbers along the line of sight. These objects are redshift 6. This is something that cannot be done with any other sources. No galaxy, no quasars. The quasar will probe, again, lines, but will be affected by the quasar itself. These are quiet galaxies, or star-forming galaxies. They're not AGNs. So these lines belong to the galaxy itself. And you can do this only with gamma reversed spectroscopy. This is, again, a summary, like H1 column density for GRBs in blue, and from quasars, DLAs in red. I don't have time to get into the details. But see, look here. Gamma reversed over here are the only players in the game. No other object can probe H1 column density at these redshifts. Moving on, this is like a metal content. These are an example of all the metal lines. These are some along the line of sight of this GRB is redshift 4. Okay. So again, all these absorption lines, the numbers you see next to it are the column density, so the amount of atoms of that specific ionization species you have near the gamma ray burst. And again, this job with the normal galaxy is almost impossible. And some of these galaxies that host gamma ray burst, if you want to do this game, just observing the galaxy are too faint. This is the R-band magnitude versus redshift. These galaxies here are detected in imaging, but they're too faint for any spectrograph, even for HST, to get any information like this. And this is an example. This is the metallicity of this sample that I showed you before, GRB-DLA. This is a work I'm working on right now. You see the metal content of the universe, as traced by gamma ray burst, is going down shallower than what you expect from this black line, which is the metal content as derived by the quasars DLA. So again, I don't have the time to go into details on this, but I want to just point out there are some points here that are only gamma ray bursts can probe these regions. Only gamma ray bursts can probe this galaxy up here where quasars cannot do that. And finally, as I said, gamma ray bursts are probably connected to the first stars. We can provide information about star formation rate. This is a plot from Osh et al. I didn't put the reference here. So these are, I think, we saw this plot, similar plot to this before. This is star formation rate density, so the amount of star formation rate per redshift beam. And you see that when you look at the Hubble deep field, that's what you get. You see that at some point around redshift 8, the star formation rate drops abruptly. But this can be also a very important thing. There are only 2 galaxies in this data point. Once you include the gamma ray burst detections, which do not select the galaxy whatsoever. So remember, I say this again. This is Hubble deep field objects, which means there are magnitude-limited survey. So there is a limit to the magnitude you can observe. Because otherwise Hubble doesn't see it. This line here is once you include the gamma ray burst population. And gamma ray burst explodes in an environment that is independent on the mass of the galaxies. So when a gamma ray burst at redshift 9 explodes, it doesn't care if the galaxy is bright or is faint, is big or small, it doesn't care. So the fact that you see a GRB at redshift 10, that means there is a galaxy there. And I can put a point up here. I don't care if I don't see the galaxy. I see the GRB, that's enough. Once the GRB is gone, I can still study the galaxies and their emission. And so when I do this, and this is a low redshift in this case, I get this nice spectrum. I see this blip here. See this? There is a continuum, and there are some blips. These blips are emission lines. And these emission lines, in particular H beta, O3, O3, O2, these give us information about the metallicity of the galaxies, the star formation on the galaxies, and there is no other way to get those information in other way. And so this is a small sample of dark GRBs and GRB-host galaxy from Dan Perley in 2013, and we are now using infrared spectrograph to expand this study and having more points at these redshifts than what you see here to have a better understanding of the GRB-host galaxy population. And in fact, last night I was working with a friend of mine in Chile, so I only slept three hours last night, and tonight again, because we are trying to get this instrument to observe these galaxies and determine what the star formation rate is from the emission lines, which are the most accurate way that you can do, as Rodriguez was saying before. You know, you prefer carbon to star, and I agree with you that it's a great way to do it. But until they give us ALMA time, that's what we have to do. We have to go to the infrared, and hopefully, if this is successful, then we have a case for those carbon to star, which I agree is a great way to do that. These are my conclusion. So Swift will keep running. I asked Judy for how long. She has the crystal ball. Swift has provided amazing science. GRB is just only one of them. We have transients. There are known sources that need to be explored. There's a lot of people interested on these different objects. I hope I convinced you that gamma ray bursts are the only hope that we have to explore in detail the early universe. There's no other way we can do that. And then again, we do have, and the community has, active programs for collecting rapid response. And this is just a summary. Swift and the gamma ray burst are actually the pioneer of the next decade high redshift universe. Hubble is here. JWST will explore down here. The GRBs are around here. We are looking for this gamma ray burst to happen at this redshift, because those will point to those galaxies that will form the first stars. And those are the galaxies the JWST wants to look at when we'll be up. So that's our goal here, is have a census of these high redshift GRBs, so when JWST goes up, it doesn't have to be like Hubble that stares a small patch of the sky forever until it gets to this redshift after 10 years. We tell them, there's a redshift 8 galaxy right there because we saw a GRB, go and look at it and tell me what it is. And that's the prototype of those galaxies right there. So those are my conclusions. I hope I convinced you.
Thank you very much. I think we might have time for one short question. Ada?
I have two questions. So it's a back to spectrum of the galaxy.
You mean the emission one? The emission lines?
Yeah.
Okay, let me get back. What is that? Oops. Let me see somewhere. Sorry. Host. It was there. I'm sure it was there. It disappeared. Ah, here it is. Yes.
Here's one. Have you measured that oxygen and hydrogen ratio?
Yes.
What's the ratio?
I think it was 3.2.
So is there, if you information about this,
The what?
shock velocity after the GRB?
No, because those are coming from the host galaxy, not from the GRB. It's all lost.
The other question about that automatic redshift.
Yes.
Is there any independent confirmation that 9.4?
No, so if you look at the contour plot here, the best solution is at 9.4. But of course, you see the 60% goes up here. So you get actually low redshift. There are very deep, at the level of the Hubble ultra deep field, HST observation of this guy, and there is no detection whatsoever, which essentially exclude that this object is a redshift less than 6. Sorry? You see here, yes. So there is a large scatter in the redshift range, depending on what it is. It's not really the sigma that you would expect for a Gaussian distribution, right? Because it's a plus, so it's plus 0.3 minus 3, right? So.
Then you cannot say it's 9.4.
Sure.
6.4.
This has the same, yes, because we only have 3 bands.
Yeah.
Yeah, but that's what I'm saying. Like again, this is the corner plot, right? So I agree with you. Although the 8.2 is confirmed, right? So you can use that one as your reference to say that. Because between this gamma ray burst and the 8.3 is only 100 million years. So it really doesn't matter.
Thank you again,
You're
Antonio.
welcome.
I invite you to ask more questions on that if you are so inclined. Now I'd like to invite up Ian Morgan, who also from Goddard, who is going to tell us about very high energy gamma ray bursts. looks like you probably are not going to be. Sorry about that, folks. There we go. And here is your...
Is that good? Can everyone hear me? All right, so my name's Ian Morgan. I just graduated from St. Mary's College of Maryland from undergrad, and I'm actually relatively new to astrophysics, just started studying in the past year or so. And I got into it because of gamma ray bursts, which is really cool. That's what really got me into astrophysics, got me excited about astrophysics. And my mentor at school just said, hey, well, I want you to do some particle physics stuff, but go study these gamma ray bursts to figure out some high energy places outside of the lab to look at it. And then I went and I found an internship with Judy to study these things with this project. So first thing that you should look at for those who know gamma ray bursts is they see very high energy gamma rays from gamma ray bursts. Well, we haven't seen any very high energy gamma rays from gamma ray bursts. That's weird. I'm absurd. Why am I saying that? Well, the thing is that the theorists, when we look at these gamma ray bursts, the emission from these gamma ray bursts, we expect to see them in the very high energy range, and we haven't. And that creates this question: why haven't we seen them? Are we looking in the wrong place? What's going on? But first, I'm going to get into a little bit of the basics and tell you about what's going on. So luckily, there has been a very good overview of gamma ray bursts, so I don't have to go into it that much. But the one thing I did want to talk about was that these things are massively energetic. It's hard to quite comprehend what's going on. I mean, these are, you can say 10 to the 54 ergs, 10 to the 47 joules of energy total output. And Judy was talking about how if you had 100% conversion of a solar mass to energy, that's what it would look like. But I don't really know what that looks like. So I take that and I wanted to put it in something that I could understand. And so I looked and I figured out that it would be about 1 quadrillion Death Stars. That's a lot of Alderons destroyed. That's a lot of energy. That's crazy. And when we see these other sources, we can see them in the TeV range. We can see them in the very high energy range. And the fact that we don't see them with these gamma ray bursts are weird. As theorists can tell us, oh, well, we're not looking in the right place. The parameters just aren't quite right to see them, but we build more sensitive and sensitive instruments. So I want to go on and talk to you about, well, what's going on? Why aren't we seeing them? So this is what a typical light curve looks like. Well, not typical. This was from GRB 130427A, which was the nearby ordinary monster. But we can see that, of course, as we expect, we see it all across the electromagnetic spectrum. And something that Judy pointed out, we can also see it in the extended emission phase. In the afterglow phase, we see it in the high-energy gamma rays. Well, it's expected that, if we're seeing it there, then maybe we should see it in that very high-energy range as well. So that's what I'm exploring. So the cool thing is, we see here, we look we can take the lessons that we learned from the Fermi Gamma Ray Space Telescope, and we can apply that to the ground-based instruments that are around to look at these TeV emissions, the very high-energy range. And you can say, all right, so what do we know about what's going on, and what should this look like? Now, I'll get a little bit more into that later on, but first I want to talk about, all right, atmospheric opacity. You'll know that the atmosphere is opaque to gamma rays, and we can't see them that well. We can't see them from the ground. Well, the thing is that that's not necessarily true. We can use these things called Cherenkov telescopes to look at them. Judy already covered some things about the Large Area Telescope. And in the Fermi Gamma Ray Space Telescope, I just like this little GIF because you can see what's going on there, but I'll pass by that. So what I'm doing to try to expand that out into the VHE range is I take this, I take a time bin, I say, all right, what do the counts look like across these energy spectra? I can fit a model to it, and then I can expand that out, I can extrapolate that out to the very high energy range. And I'll come back to some of my predictions later on. But some things to keep in mind is we see here that they're just to the very high energy range that we're looking at is between 100 GeV and 100 TeV. We're looking at them with ground-based instruments, so keep that in mind for the future. So we use these shrink-off telescopes to look at them, where we have the gamma rays coming in, creating these particle showers that create these shrink-off light cones, and we have telescopes there that image them and capture that light. And we use a whole bunch of them to figure out exactly where these gamma rays are coming from and to reconstruct them. We use something similar with water shrink-off telescopes, where instead these particle showers go through the water and create these light cones that we can look at with photomultiplier tubes. And so we've been thinking about TV emissions for a really, really long time. We had Whipple that was constructed, well, the whole idea came about and was constructed in around the late 1960s. They didn't have the camera, though, so they were trying to look, and they made some upper limits, but they didn't really get anything. And then we went into what's called the dark ages of the very high energy gamma ray astronomy. But it came back later on when they added the camera to Whipple and with Milagro, and we started seeing some TV sources, in particular the Crab. But now we use some more upgraded instruments, for example, Veritas, Magic, and Hess, which are imaging air shrink-off telescopes, that first type that I talked about earlier, and Hawk, which is just coming online, which is a water shrink-off telescope. And hopefully, by around 2020, we'll have the shrink-off telescope array, which will help us a lot in trying to visualize these things. So, as I mentioned before, there are a lot of VHE sources now. But now to get into the meat of the talk, what am I doing? How am I going about this? Well, I mentioned before that my thing was taking this, extrapolating it out to the very high energy range and seeing what's going on. What I want to see is it detectable to those ground-based instruments based off of what we get from Fermi. So, just seeing here something that what it might look like. This is what my extrapolation looks like. This just mentions the safe energy range. I'll come back to this later on, but you can see just how the extrapolation works. And here there's something about the effective area, and I'll get into why that's important. And then I can make this kind of plot where I make predictions. All right, well, in each of these time bins, would that be detectable in the very high energy range to a 5 sigma confidence? So, all right, what's important and what goes into that? How am I going about to do this? Well, I have to take into account the sensitivity of the instruments. We can see here, this is a plot that I generated from some data, that Fermi is sensitive at the lower energies, while we get Magic, Hess, and Veritas coming in as we start getting into 50 GeV and above or so, and then at the higher energies, Hawk starts to come in. CTA will be great across the whole energy spectrum, but that's not online yet. Another thing to take into account is the field of view, something that we don't think about, that needs to be expanded upon. It's really important, the field of view, because if it's not looking at the right place at the right time, then we're not going to see these bursts. They're transient events. They aren't going off all the time. We can't study them for long periods of time. So the larger the field of view, the more likely we are to catch them. That's great. Just to emphasize the point, Fermi covers a lot of the sky just in the day, so it's more likely to see these things. Veritas, Magic, and Hess, you can see where it covers them, where it can cover the sky. And then Hawk coming in, where it covers the sky. Another thing to take into account is the extragalactic background light absorption. So this is with a blazer that we're doing this. We can see the emitted spectrum. You can see as the gamma rays are coming to reach Earth, they can interact with the CMB, and we can get these electron-positron pairs, and we get this attenuation. So the higher the redshift, the more likely it is to be attenuated. So it's better to have it at those lower redshifts. So that's why we're more likely to see it from a lower redshift. Now, what does that look like to us? Getting back to that plot that I was talking about before. Keep in mind the effective area is what's going on here is that that's impacted by a number of things, where it's going on in the sky and where the safe energy range is. So Fermi looks at that first portion up to about 300 GeV or so, and the VHE range is right there. So we see that we get a lot less flux there in this range. So if we integrate we can see that right here that attenuation comes in, and we get a lot less flux there because of that attenuation. This is for GRB 130427A. So we integrate that, we take the flux, and then we can compare that to other known objects and say, all right, well, we know something, let's say the crab. How long does it take to detect the crab? What flux are we getting from these GRBs? And then we can make predictions about, all right, how long would it take us to see that? And that's exciting because that means we can make predictions about whether these telescopes should have seen these bursts. And then that lets us go on further to say, all right, well, if they should see these bursts and they're not, what's going on? Does that mean that our models are wrong? When are we going to see them? We can help figure out what are the optimized parameters for when we will see a burst with a TV instrument, and if not, what's wrong with our models? So I showed you what I've done so far. I make some basic predictions on whether these bursts will be detectable or not, and further I have to add some instruments. I have to add magic and CTA. I have to count for certain objects, like Veritas was trying to observe during GRB 130427A, but there was a full moon out it, which made it so that it couldn't observe at that time. And I have to test some other models. Right now I'm just doing a simple power law extrapolation. Hopefully I'd like to apply more complex models to that. And I can simulate bursts. I want to simulate bursts across the sky. Say, all right, where would the burst be optimal? Where would we be most likely to see it, and at what times? Now, some things to take away. Gamma ray bursts are going to be difficult to detect in the VHE. We need a large field of view. We need we need good sensitivity, and we're going to get attenuation. So if it's at those lower redshifts, we're much more likely to see it. And the thing that we really need to take away from this is that we should see the detections soon. And if we don't, what's going on? What's wrong? Is our models wrong? Are the instruments just not sensitive enough? But I'm trying to take into account each of those little bitty points about what could play into this. What would make it so that it is detectable? What would make it so it's not? So as I continue to make these predictions and we continue not to see these things, what's wrong with our models? So I'd like to thank Judy for mentoring me, great, and getting me into high-energy astrophysics. I'd like to thank Jeremy for all his help with the coding that I was doing. And I'd like to thank Crest for, for funding this project, and all the members of the Fermi collaboration for having me for the past 2 summers and really piquing my interest in astrophysics. So, questions?
Thank you very much, Ian. Nice.
All right.
Anybody?
Any questions?
I know, it's towards the end of the day.
Yeah.
Well, I could ask.
You always...
Yeah, that's right. You should go the favor. Yeah, you forgot to thank your teacher who brought you into GRB.
Oh, that's true. That's true.
Yeah. That was missing. You should go home and say thank you very much.
I will.
You'll be making a great discovery very soon. Happy to have you on board.
The extrapolation. So how how sure we are? Whenever we make extrapolation, you can have some Fermi spectra, like Fermi lab spectra.
Mm-hmm.
That's the highest we can go.
Mm-hmm.
And then there is this extrapolation.
Mm-hmm.
So
How confident can we be? Well, our extrapolations and our predictions are only as good as our models. So if we,
so basically it boils down.
yeah, that's one of the main limiting factors here.
So you can be. I'm just trying to get a sense by how much, or do you have an estimate by how much you may be off, or there may be completely no emission, right? Is there such a case that there's no TV emission at all? Is there such a possibility?
So there are some models that we would get much less flux at those TV emissions, and either that just wouldn't be observable, or there would be no emission that we'd be able to see. That would be troublesome. Or that could tell us something also about what's going on.
The non-detections can sometimes
It's
be
true.
more interesting than detections.
That's very true.
A couple of cases which are very clear.
All right. No more questions? Thank you.
For our next talk, I would like to invite Ashwin Shenoy to the podium from GWU, right here at home. This is our last talk from contributors, and then we will have closing remarks. And with that, I will provide to you Ashwin.
Thanks, Rob.
You're welcome. There you go. And you'll need that.
Good one.
Okay, Ashwin is going to tell us a little bit about a synchrotron model for GRB prompt emission.
Can you hear me?
Yes.
Not too loud, is it?
No, good.
Do you have the pointer somewhere, Rob?
I have a pointer for you right here.
Thanks.
And yeah, there you go.
So here's my talk, a simple synchrotron model for prompt emission in GRBs. So what prompted this effort? Well, I've spent the last 3 years working on kinematic effects, the so-called curvature effects, to try and describe GRB prompt emission. But while these models can explain many of the properties of the light curves, they just fail to predict the correct spectral evolution, right? So we've expanded our parameter space, we've changed our assumptions, done these models to death, no luck. So just about a month and a half ago, after a brainstorming session, we decided to follow a different approach. And these results, I should point out, are very preliminary. And by very preliminary, I mean they're less than a few days old. These collaborators, some of them haven't seen the results yet. Ada, she's going to see it today. As good a time as any to present them, right? She's a collaborator, so she's been working with me. Thanks, Ada. So, an outline of my talk. Basically, I'll describe GRBs. I'm sure you've heard about them all day. I'll focus on the relevant observations. Then I'll describe my simple synchrotron model, some of the basic assumptions, the approximations that are made for this first approach, and my results for one test case, the famous GRB 13047A, the so-called nearby ordinary monster. So what are GRBs? Well, basically, they're the most powerful explosions after the Big Bang, of course. And they're observed at redshifts as high as 8.1. So that makes them very promising candidates for studying the ancient cosmos. So broadly, GRBs are classified into short GRBs and long GRBs based on their duration. Short GRBs are believed to be produced by a binary merger event involving two compact objects. So that makes them promising candidates for gravitational wave detections. And long GRBs are believed to be the death of a massive star whose mass is of order a few 10 solar masses. They're observed at a rate of about 1 per day, primarily by Swift and Fermi satellites in the gamma ray and hard X-ray, and a significant fraction of them have multi-wavelength observations. So based on our current understanding, I present this popular model for a GRB, sometimes fancifully called anatomy of a GRB. So you have either a binary merger event or a collapsar event. They both lead to the formation of a black hole accompanied by a very energetic jet. So the initial jet is very dense and light cannot escape from it. But then you reach a region called the photosphere where light first emerges. The situation at the photosphere is expected to be thermalized. These events are very turbulent, as you could tell from the light curves. You can have multiple emission episodes. So there are possibilities that a later episode could catch up and collide with a former episode. This is what we call the internal shocks. So during these shocks, the electrons are accelerated to very high Lorentz factors, and then they emit radiation via, say, synchrotron radiation. The jet matter then coasts until it hits the interstellar medium, where it begins to decelerate, and this is what we call the external shock. And over here we see radiation in a wide range of wavelengths, collectively referred to as an afterglow. Some sample GRB light curves. Comes in all shapes and sizes. So it's very difficult to understand their properties when they look like that. However, oops, skipped a slide. Actually, I have a slide missing. Anyways, so before I go to this, what we found is that, studies for the last 2 decades have found that these complicated light curves can be resolved into simple-looking pulses. And the properties of GRB are better understood when you look at the pulse properties as opposed to the bulk properties. Compared to the light curves, the spectra are quite simple. Well, okay, that's a qualified statement. A typical GRB spectrum consists of up to 3 components. There's this thermal component, presumably from the photosphere. There's a secondary, harder component, generally attributed to synchrotron emission. And then there's this high-energy power law. So we focus on modeling the secondary component. Here I'm jumping ahead a little bit. So I present light curves in 2 different energy bands for GRB 1304 to 7A. Here's the high-energy light curve and the low-energy light curve. Notice that the low-energy light curve seems to lag behind the high-energy light curve. This is what we call a spectral lag. And also note that the low-energy pulse width, the high-energy pulse width is significantly less than the low-energy pulse width. This is typical of a large fraction of GRBs. Now, using a sample of 6 BATC GRBs with known redshifts, Norris et al. Found a tight anti-correlation between the luminosity of the GRB and the spectral lag. This and other observations suggest that both the lags and pulse widths are directly connected to the physics that drives the GRB. So they're worth studying. Coming to my model, I know there's a bunch of equations, I'll make this quick. So basically we have one internal shock where electrons are accelerated to very high Lorentz factors. The generalized electron distribution consists of a thermal part, which is modeled using a relativistic Maxwellian, and a power law, which represents the non-thermal part. We assume that the fluid magnetic field is strong and ordered, but make the additional assumption that it decays as a power law in time. So T0 gives us a measure of the duration for which the magnetic field is active, and S is the decay index. These are the 2 most important parameters in my model. The electrons then emit via synchrotron radiation. I derive the equation for 1 Lorentz factor. I'll skip the details. I then convolute that with the electron distribution and the well-known power spectrum for a single electron. So it turns out it's already very complicated, despite the simple in my title. There's way too many parameters. And for the moment, there's no analytic solution, or at least I haven't been able to derive one. I'm sure when Chuck shows up, he could try. So to get a simpler picture and to fit the model to data, I make some approximations. So this is the distribution you saw earlier for the electrons. Fits to data have shown that the thermal component, even if present, is insignificant. So in a first approximation, I ignore it. So I'm left with this power law. Now the electron power law index is directly connected to the high energy spectral index beta. And to get the right betas, a typical value for delta is about 4. So that's a very steep power law. So I can make the approximation that most of the energy, most of the contribution comes from the vicinity of the peak Lorentz factor. So I focus on that. This is a typical electron power spectrum. most of the energy is concentrated around the so-called critical energy. So I replace this entire spectrum with a delta function at that energy. Now with these assumptions, I get relatively simple equations for what the peak energy should be as a function of time and what the flux or the luminosity should be. This is in the comoving frame, hence you have the primes, but I then boost these energies and time dilate them to get to the observer frame. Coming to the data. So you've heard all about this burst, I'm sure. So basically, it's a very complicated looking light curve. But the first pulse from about 0 to 2.5 seconds is relatively clean. So we focus on that. We split this into equal time segments. And for each segment, we extract an energy spectrum. We fit the energy spectrum with some suitable function, in this case a band, extract the peak and the flux under the peak, what we call the peak flux. And we do this to every segment. We then resolve this light curve into different energy bands. We fix the lower energy band and take the spectral lag between pairs of bands. And we also measure the pulse widths for each of those bands. Okay. Jumping to my results. So, okay, my advisor, my collaborators, you can see it. Simple thing to take away, the fits look good, right? What I do is use this toy model approach to fit the e-peak versus time data. This gives me all the parameters that I need to simulate predictions for the flux versus e-peak, the lags, and the pulse widths. For some reason this hasn't appeared, but as you can see, the lag trend is recovered quite well. This was a bit of a surprise. And the slopes over here for the data and the model, the slope here is about negative 0.56, and the slope here is about negative 0.57. So that's a very close. Okay, so as I said, these are preliminary results. We need lots of simulations and tests to put these results on a concrete footing. Obviously, I've analyzed one GRB, so I have to extend this analysis to a much larger sample of GRBs. And we have extracted some limiting estimates, asymptotic estimates from a model, but given what we've seen, we cannot test these limits in the prompt emission data. But if the conditions are favorable, we might be able to place some constraints by looking at the X-ray data, primarily from the Swift XRT light curves. That's it.
Thank you very much, Othman. Do we have any questions, comments? Would the collaborators and advisors like to grill him on his results? I think maybe that we can save that for afterwards.
Yeah.
That's going to take a few years. But Ashwin, just to summarize, yeah.
What do you mean by fluid magnetic field?
So it's the magnetic field in the region of the shock.
I mean, I just
Okay.
intended fluid term.
No, not the fluid, just the decaying fluid.
Oh,
So think fluids. Think decay.
So as compared to previous similar kind of calculations, what's particularly, new specific to you? Is that the decaying magnetic field, right?
Yeah.
And what kind of new, what kind of new physics you are extracting with your, what kind of parameters you are.
So since
measuring
you're,
something or, yeah.
well, basically we want a description that can consistently give us these predictions, the ones we focused on, right? And as you know from curvature models, we get these three quite well, but the flux e-peak index is off, right? No matter what we do, we always extract an index of 3, whereas the data is closer to 1.5.
So it's kind of like fetching the standard internal colliding shock model by introducing the dependence of magnetic field.
A very simple
And
empirical idea.
apparently it works. That's
Yeah,
Okay, right.
so far. I found this out about 2 days ago.
Right, I think just to follow up on Oleg, and a lot of calculations have already been done, and so the statement was with those calculations that you couldn't explain all these four results with some basic assumptions about synchrotron emission and with a frozen magnetic field. So the difference here now is basically now if we unfrozen the magnetic field and we actually introduce the decaying field, then it does actually fit, gives you a reasonable description.
So the decay you choose for the magnetic field, is that based on some, some kind of
It's,
assumptions, or it's repeated? I probably missed that.
I would say it's purely empirical. Possible
There might be
reasons
some-
would be expansion or something along those lines. Because, I mean, S equals 2 would correspond to the flux phasing limit, more or less. Right? That's t to the power of minus 2. But the indices that we extract are closer to 0.5. So that basically...
So you might want to think about reasons why physically it can be that precisely way.
Yeah. Hopefully with Chuck coming down to GW soon.
All right. Let's thank Ashwin
Thank you.
again. And let's thank all of the speakers. Keep clapping, come on. To close out our proceedings for a couple of days, I'd like to invite Calavir Duga, the GW Astrophysics Group in the physics department here at this university, to come and give some closing remarks.
Thank
The forum is yours.
Thank you.
There
Appreciate
will be
it.
lions if you disappoint us.
Yeah. That's all right. Do I need a mic?
Yeah, if
I
you want
don't
to be
think so.
recorded, but maybe
No, I don't need to record. This is Washington, D.C. No recordings. Yes, my name is Calvary Duga, and so it is my duty to hold you here for a few minutes against your wishes. So I'll try to keep you busy. Why don't we give a round of applause to every speaker then, and for the organizing committee. So actually, if the organizing committee could stand up, actually the students in particular. So Derek and Rob and and actually we're missing Noel, right?
No, we're missing Rodrigo, Jeremy,
Yeah. And I did actually want to give Rodrigo actually a separate mention because he's actually the founder of this entity. So he's the creator. So actually, your job. Thank you. So your job actually now is to sort of go to your institution and come back another year at another place within the vicinity. So Catholic. I'm looking at Catholic maybe, Hopkins. But what we'd like to do is actually, George Mason, would like to keep this going and really talk to Oleg and Rodrigo because they've gone through the pains, they know the details, so we'd like to continue.
Just 1 second. Along those lines, I would just ask you, if you want to keep this running, talk to the new coming students. Next year there will be new students at your department. They never heard about this meeting. They maybe, are not aware of it. So just mention that to them as an opportunity to come and, learn from their peers or get some input from maybe faculty or scientists who will be present, hopefully in the future meetings from Goddard. It's a good thing. So just sort of spread the word at your institution.
Right. So while I was listening, and I apologize actually not being here for every talk, but I did try to sort of sit in most of the talks, and I collected some what I call gems. So what I'd like to do is I just sort of mention what words just came out of some of the talks. Yes. So first of all, let me, and I'll leave the best one for the last.
Is this why you didn't want to be recorded?
That's right, exactly right. So I'd like to thank Ashwin, my student, for not burning his laptop, because that's what he always does when he gives a talk. So we'll start with him. And I'd actually like to thank Rob for, being Rob. I mean, he is the only guy who could give that kind of talk with a jockey cap I've never seen him separated from that.
I saw it once. I saw it once.
Yeah, you saw it once. I think
It's
he was
really weird.
genetically engineered.
Yeah, it was
Anyway,
weird.
so that's wrong. I thought that was great. Julie, I thought, actually made a brilliant comment. She was talking about GCNs and how the connectivity goes, and she said, oh, we also do human written emails. Actually, that reminds me of some of the emails I get from my students. I'm convinced half of them are aliens. so, and then Sylvia. I'd like to thank Sylvia and her group. I think I thought the GRBs were actually discovered, in '67 by Baylor satellite, but I think now there's some evidence that maybe Picasso actually discovered GRBs back in Paris in the early
It looks pretty solid.
That's right. That's right. And then finally, Ian. Ian, where's Ian? I thought Ian actually came up with a brilliant. I think you mentioned quadrillion when you were trying to get the scale.
Yeah.
Quadrillion stars. And so, as a way to measure it, I was actually thinking, actually, a better one might be the Germany-Brazil soccer score.
That's the story of how ready to burn down.
I thought that was that's a seismic event, right?
Kill us.
Yeah. Right. And then finally, I'd like to say King Ren. I think yours came after Jeff. So he described something called DIBS. D-I-B-S. And I now, much as I'd like to give you credit for that acronym, but I've seen it before on my Rate My Professor, where it says Duga is bullshit.
Yes.
So with that, let me thank you, and we do appreciate you coming to GW. Very successful conference, and hope to see you next year. Thank you.
We are almost going to the bar, right? Yeah, but, so the first thing which came to my mind, when I was listening, is that the quality of the talks is on par, or maybe it's probably, I kind of think it's better than those at WS. So you are doing very, very good job, and I'm really actually kind of surprised looking at all the talks. And
Thanks.
That's great. And the other thing is that, when I was listening, many were not from my area of expertise, really, but it's still kind of stimulating, really, to listen to and think at the same time. And good ideas come, and that's great. And like example, for instance, Kalvir was now talking about this human, well, it started from Judy, the telegram, written by human, and Kalvir mentioned, maybe some of his are written by aliens. And so now the idea comes to my mind, those GRBs might be telegrams, aliens exchanging, So, yeah, great ideas come when you listen to other people talking. So let's keep it running, and I hope to see at least some of you next year. Thanks. And so those who are coming for the happy hour, let's meet in that area where the armchairs are. That's it.
All right.
Thank you.
Thank you. Great. Also clap. Okay, so
We don't know. We need to figure this out. But we actually need to remove these things from this area because the room is not assigned anymore to us. They can throw away the board, so we need to carry the board back to the department.
oh, okay.
Wherever.
Okay.
You find the space.
Okay.
You kind of need to do it completely because or you need to assign a person who will be people in the future.
I need that pointer.
I also need my pointer back. The one.
There's a pointer here.
Ashwin that is silver is mine.
No.
My personal one.
Not this one.
Ashwin,
Where's the
that
pointer?
that pointer you had?
Where's the box to go with this? There's a little box to go with this.
Yeah, there
Wooden
is.
box.
On this? No, man, I never took my bag with me.
No, I don't. I don't see a box.
Did you touch? Oh.
All right. For yours is right here. Oh, it has my pointer in it. All right. Cool.
Solve 2 problems.
Yes.
One that maintenance people crawling all over the place.
I know. Where was that?